Hey everybody, let's talk about free body diagrams. Free body diagrams. So if I have, let's say, a tabletop, and on that tabletop, let's maybe make it a little straighter if I can. That's a little better. I don't know. I've got a box, and physics teachers probably should take an art class, but I'm not. And what I want to do is describe all of the forces in the x direction and in the y direction. So let's make a couple of important points. First of all, my goal here is to describe all the forces acting on this object. So I'm going to add something here that someone's got a stick and they're pushing the box with a stick. Now the box is made of something rigid, like let's say it's a wooden box, but this material here, this is ice, which means that the contact between the bottom of the box right here and the table is frictionless. So the fact that it's frictionless means that if I come along with my long stick and I poke this wooden box sitting on the ice rink, that it should start to accelerate, because we know from Newton's second law, well, first of all, the inertia law tells us that if nothing happens to this box, it should stay there. So if someone pokes it, that may change its direction and its motion. In this case, we're going to get it to move. And we can even write that down. So we know that the sum of the forces in the x direction is either going to be 0 or ma or mv squared over r. Those three circumstances are the sum of the forces in the x direction will be 0 if it's not moving, if it's not accelerating. It can be moving. You can be moving but not accelerating. Here, let's make a little more room. Let's do sum of the forces in the x and sum of the forces in the y. And we're going to write these down. So before I try to say if it's 0 or ma or the third one, which is mv squared over r, and by the way, it'll always be one of those three. The sum of the forces on an object in a particular direction will be 0, or it'll be ma, or it will be mv squared over r. So let's look at our circumstance. We're pushing on this box in the x direction with a force F. So we're pushing with force F in the x direction. In the y direction, though, we're not pushing at all. But there are still forces, and we need to describe those. So what I'm going to do is I'm going to draw a little dot to represent the center of mass of my box. And I'm going to draw a downward arrow to represent the weight of the box, which is its mass times the acceleration due to gravity. So as a reminder, Fw equals mg. And it is a vector, so it's down. But the thing is, it's not accelerating in the y direction. It's not even moving in the y direction. Since it's not moving, we can definitely say it's not accelerating, since this is an inertial reference frame, but that means there must be an upward force. Oh, goodness, that's a terrible drawing. There must be an upward force to balance it out. That's a little too long, y'all. What we want to do is try to indicate the weight and the normal force, N. So I'll often write Fn as just N, meaning normal force. Reminder, normal means at a right angle to. So the normal force is at a right angle to the tabletop. And what we're saying there is that the normal force is pushing up and the weight is pulling down. And this is Newton's third law in action. So gravity is attempting to pull the box down, but because the box is rigid and because the table's not going anywhere, the table is supporting the weight of the box. So it's pushing up with a force that matches that of the weight. But we don't have to actually just write that down. We can actually use Newton's second law to get at that idea. So let's revisit our sigmas here. Sigma F in the x, sigma F in the y. So I'm saying there's no friction on the ground, and I'm pushing with a stick F. So that means the acceleration in the x is m times a, where a is whatever acceleration I'm giving it by pushing it with this stick. So it's ma. But in the y direction, the sum of the forces is 0 because there's no acceleration in the y direction. In fact, it's not even moving in the y direction. Remember that x and y are orthogonal to each other, so whatever's going on in the x direction and whatever's going on in the y direction, they're independent of each other in terms of their vector nature. By the way, the reason we write this down in the x and the y so that we can treat each of the components, the x and y components, independently, and the only thing you need to do to determine whether or not it's something what its vector nature is, if you know the axes, is to label the axes. So I always call plus the direction of motion. So since it's moving that direction towards what we would think of as plus x if it were the x-axis, let's call that to the right, let's call it plus. And since I have no other reason not to, I'm going to call up positive. So I tried to draw my diagram so that the Cartesian coordinate positives that we're used to can like apply to our particular drawing. So this kind of drawing, by the way, should always be done. This is known as a free body diagram. You've got this object here and we want to draw all the forces on it. And the reason we want to draw all the forces is that it helps us to write down the sum of the forces. Okay, so to revisit it, now that we've picked a positive, up is positive, right is positive, now that we've labeled all of our forces, we've got up from the table, down from weight, and to the right is being, there's a force being applied to the right from a stick. Now that we have all those in there, we can actually write this like this. The sum of the forces in the x direction is ma, and we can, now that we've said it's either 0, ma, or mv squared over r, you do that first. It's either ma or 0 or mv squared over r. In this case, it's ma because it's being accelerated. In this case, it's 0 because it's not being accelerated. And the only time something would be mv squared over r is if it's being forced to move in a circle. So we know that in the x direction, the sum of the forces is ma. Now I can look back at my diagram and write down all of the forces. And I'll make it positive if the force is in the direction of my acceleration, or the one that I've called positive, and it is. And there are no other forces in the x, so I'm done. I'd call it negative if it went the other way, which we're going to do here in the y. So normal force, again, you can call this F sub n. I typically call it capital N. Normal force is up, so I make it positive, and the weight is down, so I make it negative. And we can actually, we'll call this number 1 and this number 2. Let's rewrite number 1 down here, ma equals F. Well, if I knew literally how hard I was pushing, and I knew the mass of my box, I can figure out the acceleration at this point. So if I knew that the force were, say, 100 newtons, and I knew that the mass of the box were, say, 5 kilograms, then I can figure out the acceleration. Wow. I can figure out the acceleration by the force divided by the mass. So 100 over 5 is 20, and the units are newtons. Now you can write this as, the units of force are newtons, which I skipped. I just kind of ran right past that. This is acceleration, so that's m divided by s squared, meters per second squared. This is a newton. I guess I should capitalize it since it's named after the dude. And it's our unit of force. And you can tell from this diagram here, or this equation, excuse me, that if the mass were measured in kilograms, you use square brackets for your units, and the acceleration were meters per second squared. And I'm telling you, the definition of a newton is this. So that's what a newton is literally defined to be, a kilogram meters per second squared. Again, you put the square brackets around it in physics class when we want to refer to them as units and not as variables. And by the way, that is a pretty extreme acceleration, okay? 20 meters per second squared is significantly more than free fall, which is 10 meters per second squared. It's a double that. So that is seriously being accelerated in the x direction. So let's hope there's plenty of room on this ice for this thing to move, because it's going to keep going until something else pushes on it. It's going to reach a final velocity when I stop pushing with the box, and whatever that velocity is, it's going to have it until it hits something else, like the side of my ice rink. Okay, so that was equation number 1, and now let's just, typically you only do one axis, but we already, that's a mess. We already wrote down the x, so we should finish this out. So the sum of the forces in the y direction was 0, which equaled our normal up minus the weight down. And it's not surprising that if I rearrange this, I get the normal is the weight. That is to be expected. So if you already knew the mass, I could figure out the normal force right now. It's just the weight. So that's not a terribly important piece of information for this problem, because without friction, the fact that the normal force and the weight are counteracting each other almost makes them irrelevant to the problem. Really, the only kind of motion that's going to happen now is in the x direction. Since there's no friction, the normal and the weight can't actually impact the motion of the box at all anyway. So that's sort of an introduction to free body diagrams with a single box along a single axis with a single force being applied.